All right, so last class was dedicated to particle equilibrium. So particles basically was just a single point. Any force applied to that single point, get point of application doesn't really matter because again, it's assuming it's just a point anyway. So there's really only one point you can assign that force. And what that does is it neglects any sort of rotation. So when we want to get into now actual extended rigid bodies, so big objects, anytime I push on something, so if I have this pencil here, for example, if I push on it, it's going to want to make it move upwards, which we saw before, but it could also make it want to rotate depending on how it's attached over here. And so that's why we want to deal with rotation now. And so the first thing to do when dealing with rotation is to talk about moments. So start off just in 2D. We'll get to 3D later. But if I apply any moment, so if I apply a force to any object, again, like I have with this pencil, I'm applying a force. It could either make it want to translate, so move up and down or left and right, depending on which way the force is acting on it. Or it can also make it want to rotate, or even more fun, it can make it want to do both. So depending on where this force is acting and what else is going on inside my pencil or whatever other object I'm dealing with, there could be some tendency to rotate. And so this force acting on my object could make it move or could just make it want to move. So if I'm, again, pushing on this wall, for example, behind me, I'm making the wall want to move, but because the wall is fairly solid, fairly sturdy, it doesn't actually move. So same thing with moments. When I push on something, my pencil, for example, it could make it want to rotate, but not necessarily rotate. And so again, anytime I have a force that's causing a tendency to rotate, that is called a moment. Physics class usually called torques. For some reason in engineering status class, they're called moments. They're basically the same thing. Not sure exactly what the difference is. So it's kind of the same thing as a torque, force acting at some distance to cause rotation. And then kind of good news, bad news scenario for moments that we'll see is that moments can be evaluated at any reference point. So again, if you're dealing with torque or moment, you're dealing with a force times a distance. That distance could be to any point I want, which is good, but it's also bad. Now, obviously, the good thing is I can pick any point I want. Bad thing is depending on which point I pick, the problem and the math is going to be either harder or easier. So that's kind of the good news, bad news. You can pick the easy point, but you need to know what the easy point is. And so that's going to come with some practice, as we'll see. So again, standard formula for moments is force times distance. And specifically, I want the perpendicular distance from the force to that point, whatever I'm going around. And that perpendicular distance is also called the moment arm. So again, whatever point I'm dealing with, perpendicular distance to the line of action of that force gives me that moment arm, and the force times that distance gives me the actual moment. Officially, moments are vectors, just like forces, and so the direction is going to matter. In 2D, for now, the direction can be taken into account using either clockwise or counterclockwise. If I have a 2D system of forces, that's the only way something can rotate. It can't start rotating in and out of the page because it's no longer 2D in that case. So if I have just 2D forces, the only options I have are clockwise, which is negative by convention, and counterclockwise, which is positive by convention. And that's kind of the standard math conventions anyway. Angles always go counterclockwise is positive. Same thing for moments. Counterclockwise is positive. And again, just like forces, usually for equilibrium, for example, I want to take the net force, the sum of all forces. I'm also going to want to have a net moment. So I want to find the sum of all the moments acting on an object. And so to do that, it's very similar. For net forces, I just take all the forces and add them all together as vectors. Technically, for moments, you do the same thing. Take all the moments and add them all together, again, technically as vectors. My moments are caused by forces. So even though I say I'm taking all the moments, I have to realize that what I really mean by that is take all the moments produced by all the forces. So this force F1 acting up here is going to cause some moment m1 around point A. This force over here, F2, is going to cause some moment m2 around point A. And this force F3 down here is going to cause some moment, again, around point A, called m3. And so to find the total moment, I just add them all together, m1, m2, and m3. Now usually what I do when I do this, when I'm taking the sum of the moments, I usually put a little subscript down here at the bottom of m, because that tells me which point I'm actually taking this around. As I mentioned previously, you can take any point you want. And so when you're communicating your solution, you want to tell me or tell other people or tell yourself even what point you're actually taking this around, because you can choose any point you want. So I always like to have a little subscript down there letting me know this is around point A, so that I know when I go back and check my work, that's what I was doing. It wasn't for some other point. So again, to find these moments, moment is just force times perpendicular distance. So I have a perpendicular distance d1 from point A to F1, some perpendicular distance d2, again from point A to F2, and some perpendicular distance d3 from point A perpendicular to the line of action of F3. And so those are my 3 perpendicular distances for my 3 forces causing moments. And then the moment m1 is just equal to that force F1 times that perpendicular distance d1. My moment m2 is just the force F2 times the perpendicular distance d2. And my moment m3 is just F3 times the perpendicular distance d3. However, I do want to take direction into account, because again, these are vectors. So I do also want to take into account whether these are going clockwise or counterclockwise. So essentially what I do for this is I look at this and I kind of pretend these perpendicular distances are like strings. So this distance d1 is like a string attached to point A and attached to the force. And then this force is going to move whatever direction it's pushing or whatever direction it's pointing in. And so this force F1, again, pretend it's attached to a string here, is going to move around in that direction. That direction is counterclockwise. So this F1 times D1 is positive when I write it over there. Similarly, F2, I pretend is attached to the string D2, attached to point A. He's going to go around in that direction. That is clockwise. So in this case, I have a minus sign in front of F2 D2 because he's going clockwise. And then similarly for F3, going to go that direction counterclockwise, so positive around A1. In the previous case, it may or may not have been easy to find those perpendicular distances. Sometimes it is, sometimes it isn't. We'll see an example fairly soon here where it's actually very hard to find a perpendicular distance to the line of action of a force. It's actually much easier to use what's called Varignon's theorem. So Varignon's theorem essentially says that I can take a force, I can break it down into x and y components, and then kind of treat those two x and y component forces as their own individual forces. And then the total moment caused by that one force is just the algebraic sum of those two individual moments produced by those two individual forces, the two components. So it's kind of like what we did on the last slide, except that I take one force, break it down into x and y components, and then add those two x and y components, they're the moments from those two x and y components, add those together to get the total result. So this is my example that I was talking about. So I have some force here acting at some angle on this upturned cantilever beam at this point here. So if I look at the line of action of this force, come straight down over here, perpendicular distance to A is this d perpendicular here. Now, based on the geometry of this problem, I'm probably given this this distance for this horizontal part of this cantilever beam. I'm probably given this distance dy for the upturned part of it. So I know the two lengths of my cantilever beam. I know this angle, but then trying to figure out, okay, where is this line perpendicular to this point A over here is a bit difficult. So easier thing to do, instead of doing that, I can take this force F, break it down into X and Y components. So essentially, F cosine theta gives me Fx, F times sine theta gives me Fy. I now have vertical and horizontal forces, and perpendicular distances to vertical and horizontal forces are horizontal and vertical distances, which again, I probably know. I probably know this dx, I probably know this dy. And so in terms of geometry, this is a much simpler thing to do. Just break down my force using sine and cosine, and then my perpendicular distances are easy. So sounds like you're making more work for yourself because you're taking one force and breaking it up into two, but you are saving yourself a whole lot of geometry and a headache there. So even though you have to do two of these, F times D's, they're fairly easy to find F and to find D, as opposed to having one very difficult D perpendicular. So again, for this point A1, for this moment around point A, I'm going to have some force, Fx, times its perpendicular distance. So again, if I look at this line of action, that dy is the same as this dy, so that's my perpendicular distance to that line of action of that force. And then again, if it's going around point A, it's going to go around in that direction because that's the way this force is pointing. And that is counterclockwise, so that guy is positive. And then similarly, I have this force Fy going down. As it goes down, distance perpendicular is dx, obviously, and then that's going to make it go in that direction as it starts to spin around point A. And so that is clockwise. So that's why there's a minus sign here. So normally Varignon's theorem is you add the two, but you want to add them with the appropriate sign. So this sign is just saying that it is a negative moment produced by, so this force Fy is producing a negative moment around point A, a clockwise moment around point A. So those are moments in 2 dimensions. 3 dimensions is actually not that different. Official definition of a moment, as I said, it is a vector. We've kind of been playing with the vectors and just saying clockwise, counterclockwise, plus and minus. That takes into account its direction. Officially, a 2-dimensional moment is actually in the 3rd dimension. So the 2D moments we saw before are actually moments in the z direction. Clockwise is actually negative z direction. Counterclockwise is actually positive z direction, which is why we have those conventions. Officially, to find the moment, I take the cross product, r cross f. So my moment around some point O is the distance r. So this vector r is some position vector starting at point O. So wherever I'm taking the moment around, starting there and going to the line of action of the force. That position vector crossed with the force itself gives me the actual moment. And remember, cross product is very dependent on the order. So make sure you do r cross f instead of f cross r. I have the habit of when I do 2D, I do f times d or f times r. But when you do the cross product, make sure you do that opposite order. Make sure it's r cross f. Otherwise, you'll have the complete opposite moment you want. It'll be completely backwards. Another nice thing about this is the position vector r can be any position vector that starts off at point O and goes to the line of action. So if in this case here, I have 2 of them, I have R1 that goes from O to the line of action, R2 that goes from O to the line of action. If I take R1 cross F, or if I take R2 cross F, it gives me the exact same answer for the moment. So that's another nice thing about moments. You can take any position vector you want, as long as it starts on the point you're taking the moment around, in this case point O, and goes to anywhere on the line of action of the force. The cross product, the geometry, it all works out. And in terms of direction, if you remember cross product of 2 vectors is always perpendicular to those 2 vectors themselves. That's why if I have a 2-dimensional system, all my distances and forces will be in the xy plane, which means that my moment has to be perpendicular to the xy plane, which is the z direction. And if you think about that, again, coming out of the page is positive. Again, you use your right hand rule. Right hand, if you point it at yourself, point your thumb to yourself, you see that your fingers are going counterclockwise. So that's why that is positive. That's why out of the page is positive. If you have a three-dimensional version, again, you can either find the direction by the right-hand rule, or you can just do the cross product, and the cross product will give you components which actually have the direction embedded within them. So doing that cross product, you have to use the equation we had before, day 3 when we talked about vector cross products, or use the determinant formula, whichever way you want to do it. In this case, I specifically have r as my first vector and f as my second vector. So just kind of replacing the notation with r's and f's, I get this kind of long equation for my moment. So again, r goes from point O to the point of application or anywhere on the line of action of point F. So I have some x component, some y component, and some z component for each individual r cross f. And then, of course, if I want the total moment, so the sum of all the moments from all the forces acting on my object, I can just take all of them added together again as vectors. So r cross f for every single force from point O to that force. Add them all up, and that gives me the total moment around that point. So kind of showing you that this is the same as what we did in 2D. I can take the same scenario I had before when I used Varignon theorem, and I can use this big long 3D equation to show you that it reduces to the same equation we had before. So because, again, everything here, all my distances, so r, for example, rx will be dx, ry will be dy. Then my forces fx will actually be negative fx because it goes to the left. Fy will be negative fy because it goes down. So if you do it the three-dimensional way, you actually have to worry about which way forces are going. If you do it the two-dimensional way, you just worry about which way those forces are pushing around point A, like I did before. So again, pretend they're on a string, and which way are they going around that center of rotation, essentially. So for this guy, I have 0 z components. So no z component gets rid of that, no z component, no z component, no z component. All I'm left with is the k component, again, which is my z direction, like I said before. I have rx times fy, ry times fx, and again, rx is the same thing as dx. Fy actually goes down, so negative fy. Ry is dy, and then fx is actually negative fx going to the left. And so plugging that in for my z component gives me moment around point A, fx times dy minus fy times dx. Same equation we had before, doing it the way I do it for two-dimensional vectors. So whichever way you want to do it, it's going to work out. It's just a matter of, if you're doing it in 3D, make sure you're taking your left, right, up, down directions into account. If you're doing it in 2D, don't take those into account, just take into account clockwise or counterclockwise. And then last thing for moments, so sometimes it's useful to want to know what the moment is around a certain axis. So moments, again, are things that want to cause rotation, and they want to cause rotation around certain axes. So if you want to know how much rotation is around a certain axis, a useful thing to do, or that's a useful thing to know. So you want to know how to calculate that. Easiest way to calculate that is to, once you have the actual moment in any arbitrary direction, then take the dot product with the unit vector in the direction you care about. So if I care about, for example, the moment around the x-axis, my unit vector EA here will essentially just be I, just the x-axis. And if I dot that with the moment I found before, that'll give me the component in the x direction. So that'll give me the moment or the rotation around that x-axis. Of course, you can do that for any axis you want. I can do that. Doesn't have to be x, y, or z. It could be some combination of them. Whichever case it is, just use that unit vector in that direction, dot product with the moment you found before. If you didn't find that moment before, you can just kind of take the total determinant. So before, using the cross product, you had ijk, If you dot something with a cross product, you just replace ijk with whatever you're dotting it with. So in this case, the unit vector, EA x component, EA y component, EA z component, and end up with a very similar equation. But again, I, j, and k are replaced with EAX, EAY, and EAZ, and that'll tell you the component of the moment around that axis. So those are moments. Those are things that help us to calculate rotation. And so those are the things that we're going to need to know when we start talking about extended bodies. So we'll talk a bit more about those in the next video.